some cases we don't know how to make those.
Can I turn this?
I do think that there is a huge advantage from being able to run this basis in C++.
Yes. I think it's definitely there. I think it's maybe that's the.
Give him 1 second to get set up here. Good. All right. So our next talk will be by Tao on scalable zero-knowledge proof made easy.
Hi everyone. Thanks for sticking around for this final talk of the session before the reception, and for taking the time to listen to this. This will be more of a systems talk than I think the talks in this workshop so far, but hopefully you'll still enjoy it. I want to kick things off though with a quick shout out to Chungyan Ma, who was really the lead author on this work and brought to bear both the background in implementing zero-knowledge proof systems, as well as some compiler expertise that was really crucial to bringing this whole system together. He did this in completion of his master's work. He's unfortunately now at Citadel, but he's still continuing to work with us on this project. And I just want to give him the credit where credit is due. And today I'll hopefully do justice to his work. OK, so how many of you have heard of zero-knowledge proofs before? Great. You have all the background you need to understand this talk, or at least the zero-knowledge proof component of this talk. Just to make sure that we all are starting from the same basis, I'll give you a little bit of a background on zero-knowledge proofs. These allow someone to prove the validity of a statement without revealing any other information, just the fact that the statement is true or false. To be a little bit more formal about it, we suppose that we have some function f and a public input x, and a prover has done a whole bunch of work and come up with a private input, or witness, as it's often called, w, that satisfies f of xw. And now the prover wants to prove to one or more verifiers that they have this witness. So we have these two parties in our system, a prover, which operates on f, x, and w, and will generate some proof pi, and a verifier, which operates on f, x, and the proof pi, but not w, and will either accept or reject the proof. A zkey will also ensure some additional features, like completeness, meaning honest provers will convince honest verifiers, and soundness, meaning that cheating provers won't be able to get away with it. Well, there's a probability component, so they won't keep getting away with it. And on top of that, we will look for our witnesses to hide for our proofs to hide any details of the witnesses, so that the verifier won't be able to determine the witness from the proof. And we'll also be interested in proofs that are small and making sure that verification is fast. So that's nice and all. We have provers, we have verifiers. It turns out that this is a very general formulation. And in fact, every single problem in NP admits some zero-knowledge proof. But perhaps more importantly for practice, recent advances over the last decade in zero-knowledge proofs have made them practical. And that's led to a whole bunch of real-world applications of zero-knowledge proof systems, such as in blockchains, verifiable machine learning, electronic voting, static program verification, verifiable image editing, verifiable databases, electronic cache systems, and so on and so forth. And with all those new applications of zero-knowledge proofs have come a lot of new implementations of zero-knowledge proof systems, which have resulted in something of an explosion of these systems in terms of their size and complexity. Generally speaking, these new zero-knowledge proof systems aim to improve on their predecessors by allowing the proof sizes to be smaller, by speeding up verification, by speeding up proof generation, by offering better cryptographic properties. I'll say a little bit more about that later in the talk. One remaining problem, though, is that despite these advances, proof generation in practice still remains slow. And by slow, I mean like 100 times slower than verification. So in one particular context, in the context of digital wallets, that can mean that a single transaction can take order of minutes in order to generate the necessary proof. And that can really hinder the usability of that system. So that performance bottleneck has led researchers to explore ways to accelerate zero-knowledge proof generation, not just through algorithmic improvements, but through other means of acceleration, such as using parallelism with multi-core CPUs, or accelerating it with GPUs, or using FPGAs or ASICs or other custom hardware to speed things up. The problem, however, is that these zero-knowledge proof algorithms can be challenging to accelerate for a variety of reasons. First of all, generally speaking, if you want to accelerate this on custom hardware or even on a GPU, you generally have to re-implement the system in some hardware-specific programming model that was not the language that you used to implement it in the first place. And so that requires a lot of engineering effort. Moreover, as these new algorithms come along, they have a tendency to introduce new protocols which are based on entirely new theoretical underpinnings, which mean, from a practical standpoint, that all the code that was written before to speed up a zero-knowledge proof system is kind of worthless for the next one that comes along. Furthermore, practitioners who implement these things often want to use complex programming patterns in order to simplify their implementations, including higher order functions or even recursive proof generation. And those aspects can be difficult to speed up, especially with, say, a library-based solution, where you imagine just writing a library of really fast kernels. That actually doesn't tend to work so well for some of these zero-knowledge proof methods. So in this work, we asked ourselves the question, well, can we just use task parallelism? We love task parallelism. Can we just use task parallelism, maybe with some extensions, and will that work in this context? And the answer is, yeah, it works great. So we developed this system called Zera, which extends OpenSilk, that's why I'm here, to provide language support for accelerating zero-knowledge proof systems on CPUs and on GPUs. Zera admits spawning, syncing, parallel loops. It allows for nested parallelism, as shown on this slide. It allows for parallel reductions and parallel scans, and also provides facilities for offloading computation onto GPUs. And the idea is that Zera aims to accelerate the common patterns that we find in these zero-knowledge proof systems when they're just written in a single task parallel source code. So we put together this system, providing language supports to accelerate these zero-knowledge proof code bases. And we gave it a try by using Zera to implement the Shockwave ZK snark, and I'll define a little bit more about what that is in upcoming slides. And we evaluated its performance against existing baselines, including some single-threaded Rust and C++ baselines, the existing multi-threaded Rust baseline, which is parallelized using Rayon for multi-core CPUs, as well as some manually written CUDA. So what we found overall was that Zera really helped implement this accelerated version of Shockwave. Parallelizing Shockwave with Zera just required 93 high-level annotations onto an existing 7,000-line C++ code. And those 93 high-level annotations paid off. On large inputs, we observed that Zera's Shockwave implementation runs around 24 times faster than the existing Rayon parallelized Rust baseline, and is within about 1.6x of manually written CUDA, which required an additional 3,000 lines to write. Yes?
So you say you added 93 annotations. How tricky was it to actually find where those annotations were? Like, can you imagine now an AI agent doing this work? Is it like mechanical, or is it actually something that requires an expert who understands in depth what's going on?
How tricky was it to insert those 93 high-level annotations? That's a great question. I'm not sure of the exact answer. I suspect that Ching-Yen had a lot of expertise in implementing these systems, and so pretty much knew where to look. There are also a lot of common patterns in these zero-knowledge proof systems. When we dive down far enough, we find those patterns, and the way to parallelize those patterns, some of it is pretty well known. The other advantage of these task parallel language frameworks is that it's relatively easy to try things to see, can I parallelize this computation? And then you can run, say, the Silk race detector to see if you accidentally introduce a race bug, or if there's further work you need to do to parallelize things effectively. I do think it is remarkable that you don't need a lot of code change in order to perform this acceleration. And whether I believe an LLM would be able to pull this off without just lots and lots of examples, I'm not sure. But I do think this is an important step. Other questions so far before I continue? Yeah?
Why is the Rust so bad?
Why is Rust so bad? OK, well, so first off, it is running on CPUs. There's that. The Rayon is a library implementation of work stealing, which will come with overheads that we get to avoid with the compiler support in OpenSilk. Beyond that, I think for more specifics on the gap between the CPU parallel Rust and CPU parallel Xera, I'd have to defer my co-authors. We also know that in general, Rust tends to be a little bit slower than C++, but I don't think that would account for the entire gap here.
But here the C++ and Rust are exactly the same, right?
So
It's the blue and purple lines, right?
yeah. So on the single-threaded baseline, yeah. I think there actually is a gap between those two lines. It's just very, very small. So that's why I don't think that's what's really causing this gap in terms of performance. Cool? Yeah.
So how specific is the parallelizing here to, or the annotating to the fact that you're doing a zero knowledge proof? I mean, if someone who was good at this and now they had a graph algorithm, would they be able in the same amount of time find the same number of annotations, or is this something specific about zero knowledge proofs you're taking advantage of?
So how specific is this to zero knowledge proofs? I really like that question. In fact, I like that question so much that I include a section of the presentation all about it, because we start to explore that question. We've started to explore that question now. If it's OK with you, I'd like to defer it to the end, where I'll have more. I'll have some slides to show. But yeah. All right. So at this point, I want to dive into some of the details of Xera and how this works.
On the last slide, why do you have a parallel C++ version here?
Why do we have a parallel C++ version? I think the closest to a parallel C++ version is the Xera CPU version, which doesn't use any of the GPU offloading. It just uses task parallelism. OpenSilk supports extends C++. Beyond that engineering effort, if you want to parallelize C++ directly, that tends to be quite onerous unless you have some higher level language support. So, yeah. All right, so for the remainder of this talk, I'm going to characterize a little bit more about what we find in zero-knowledge proof computations that let us accelerate them with this framework. And then I'll talk a little bit about how Xera works. That'll be the more systems-oriented part of this talk. And then finally, I'll come back to your question of how well does this generalize beyond zero-knowledge proofs? OK. So to characterize the zero-knowledge proof systems we observed, we focused on a popular system for zero-knowledge proofs today called ZK snarks. So ZK snark is short for zero-knowledge, succinct, non-interactive argument of knowledge. Yeah, that was my reaction too. What does this mean? OK, well, we still have the same general goal as before. We still have this prover and this verifier. The prover has a function f and a public input x and a private witness w that satisfies f of x w. It wants to prove that it has this witness to the verifier. It doesn't want to reveal the witness. Fine. OK, the zero-knowledge part means the proof from the prover shouldn't reveal anything about the witness w. The verifier shouldn't be able to figure out the witness w from the proof. Succinct means that we're looking for short proofs and fast verification. More formally, we're generally looking for something sublinear in the size of the function and the size of the witness. So that's actually faster than traditional NP verification. But that's what we mean by succinct here. Non-interactive means that after the prover delivers the proof to the verifier, there is no further interaction between these two parties. You deliver the proof. The verifier can do its thing and will accept and reject. There's no back and forth as in interactive proof protocols. Just that one delivery. Finally, ZK snarks satisfy an argument of knowledge, also known as knowledge soundness, which basically says that assuming the prover is computationally bounded, it must have known that witness in order to construct the proof. That's the intuitive definition. You can formalize that definition with probabilistic polynomial time adversaries and extractors. That won't be important for today, so I won't go through that aspect. But that's essentially what it means. You're computationally bounded. That means in order to make this proof, you had to have known the witness. So broadly speaking, how do these things work? Well, essentially, the prover starts by converting the computation of f of xw first into an arithmetic circuit with a bunch of gates and values on edges. And then it converts that circuit evaluation into a bunch of polynomials over a big finite field. And those polynomials comprise the proof that it delivers to the verifier. The verifier will then check the proof by evaluating those polynomials at a few random points and testing for polynomial equality. And as long as you choose this polynomial formulation very carefully, and you use the right finite fields, and maybe the right bilinear groups, and as long as you inject randomness in just the right ways, you can in fact satisfy all of the properties of a ZK snark that we saw on the previous slide. Now, getting more specific than this becomes really hard, because this is the part where things get complicated and diverse. It turns out that there are a lot of ways to build a ZK snark. And researchers are continuing to find new ways to build ZK snarks that satisfy all these properties. The table here summarizes some of the approaches discovered over the last decade. So some of the approaches are based on probabilistically checkable proofs. Others are based on interactive proofs, or more recently, polynomial interactive oracle proofs, PIOP. They use different constraint systems, such as the rank 1 constraint system, or layered circuits, or Plonk. Their proof mechanisms are based on various techniques, such as quadratic arithmetic proofs, the GKR protocol, the KZG, polynomial commitment scheme, or the inner product argument, or Reed-Solomon codes. That's what FRI is all about. They're based on different underlying problems, like Q-type knowledge of exponent, or hashing, or bilinear pairing, discrete log. Some of them required a trusted setup step. Some of them are so-called transparent, and they offer different bounds on the time for the prover to generate the proof, the time for the verifier to check it, and the size of the proof. And this diversity continues to grow. Researchers are continuing to find new ways to construct these ZK snarks, which will offer different bounds and different cryptographic properties, which is part of what makes it so hard to accelerate these things. So given the diversity of these code bases, how do we accelerate them? How does Zera approach this problem? Well, what we did is we dug deeper. We said, OK, these are the protocols and schemes that these systems are using, but let's survey a whole bunch of ZK snarks over the last decade and just see what are the parallel patterns therein that are crucial for actually performing the computation. And we found that across these ZK snarks, there are really just 5 key parallel patterns that were core for proof generation. And they're shown on this slide. So all of these systems use some form of map, zip, and reduce over some custom type in order to perform the basic vector or polynomial arithmetic underlying the whole system. Some of them do the number theoretic transform, or NTT, which is an FFT-like computation generally used for ensuring soundness. Others use Merkle trees, often for succinct commitments. Some use sparse matrix vector multiplication for the inner product arguments, or linear time encoders. There are some that use multiscalar multiplication, MSM, for creating commitments, although what we're finding is that this pattern is actually less used in more recent ZK snarks, possibly because MSM turns out to just be really computationally expensive. OK, so given this relatively small subset of parallel patterns that are crucial to these systems, Zera aims to accelerate those patterns by providing a task parallel language framework that supports parallel tasks, parallel loops, nested parallelism, and reductions and scans on custom types, as I mentioned before. Here I have a reduced version of that sumcheck pseudocode that I was showing before, just to highlight some of the language properties in Zera including, in this case, 2 nested parallel loops where the inner parallel loop has a GPU offloading annotation, allowing it to be run as a GPU kernel. And notably, the Xera supports parallel reductions on custom types using the same linguistic mechanism for reductions for both CPU side code and GPU side code. So there's a reduction mechanism that can be used wherever you want to operate on this type. Good so far? Cool. So how do we build this? Well, to accelerate these constructs, Xera extends the OpenSIL compiler, hence the shirt, which uses LLVM and an extension to LLVM we've developed called Taper to allow it to effectively analyze and optimize parallel code. So the idea with Taper is that this is a different representation of parallelism for compiler analysis and optimization, where it adds 3 instructions to the traditional compiler IR to make task parallelism really easy for traditional compiler analysis to deal with, thereby unlocking the compiler to do all kinds of useful transformations on parallel code. Now, to actually accelerate these things, especially on GPUs, Xera builds on another extension to OpenSilk called Kitsuna, which we've been developing in collaboration with Pat McCormick's team at Los Alamos for the past few years. Kitsuna essentially adds GPU support to the OpenSIL compiler. More concretely, Kitsuna dives into the compiler at this taper lowering step, which transforms this representation of parallelism within the compiler into ordinary LLVM IR. And at that point, Kitsuna will identify parallel loops within the code and will transform those loops into GPU kernels, plus kernel launches and some additional code to actually run on the host side, or to run on the host side and execute those GPU kernels.
It'll do that because there was a directive to offload?
Currently, it does this because there's a directive to offload, yes. We're not going so far as to automatically recognize parallel loops that we think would be good for GPUs. That's future work. OK. So Xera combines OpenSilk as well as Kitsuna and its support for GPU execution to support nesting CPU or combining CPU and GPU parallel loops in one specific way. So Xera allows the innermost loop to be a GPU parallel loop, and outer loops beyond that can be CPU parallel loops, as illustrated here. What happens in this case is that the outer loop will be scheduled using randomized work stealing, for example. And when those workers encounter the code of the inner parallel loop, that will have been converted into a GPU kernel. And so those individual workers will launch the GPU kernel when they encounter it. And then we'll synchronize that kernel later on. But with multiple parallel workers executing the outer loop simultaneously, this means that you can have multiple GPU kernels running simultaneously. To manage that, we use separate GPU streams, or more specifically, CUDA streams. And internally, Xera uses a special GPU stream silk reducer object in order to manage all of these parallel kernel launches. So the CPU workers can launch these kernels in parallel. The reducer will make sure that independent streams are available for the distinct workers. And as those workers finish their computation, those streams will be synchronized appropriately. This approach, although limited, works well for ZK snarks because the inner loops tend to be large compared to the outer loops. So the outer loop will have order of a dozen or dozens of iterations, whereas the inner loop will have millions of iterations. And when you have that balance, nesting the parallelism and nesting the GPU launches this way can pay off. Yes?
Does that also deal with minimizing the amount of data transfer between CPU and GPU?
Does it deal with minimizing data transfer between CPU and GPU? This alone doesn't. The thing on the slide after this will address that question. Is this actually worthwhile at all? So first I want to address the question, is this actually worthwhile at all? If you have so much parallelism in this GPU kernel already, is it even worth doing the additional parallelism on the CPU side? Turns out yes. So we observe that this CPU-GPU collaborative parallelization is effective at keeping the GPUs highly utilized. And we evaluate that by running the Xera GPU code on varying numbers of CPU workers. And in general, we observe roughly a 1.5 to 2x speed up from using CPU parallelism to launch GPU kernels simultaneously in this way. Yeah?
Is there some inter-stream locality you're missing out of this kind of?
Is there inter-stream locality we're missing?
Run them in the same stream.
So we know from the fact that the outer loop is parallel that it is legal to execute those in distinct streams, and that's how the distinct streams is how we're supporting the parallel execution. Whether they're data locality trade-offs, I think that's up to the implementation of the ZK snark in this system in order to ensure data locality with parallelism.
It's potentially read-only, maybe, locality that you might be.
It's possible, although it's worth noting that on the systems we've evaluated on, there's only one GPU.
Right. Still on the caches and on the SMs.
Oh, sure. Yeah. So I'd say we haven't observed any locality loss from this strategy, but there's also still a gap between what we're able to achieve and manually written CUDA. Okay. I want to come back to your question about memory. Because one of the most important things about getting performance on GPUs is dealing with memory. GPU memory is not the same as a system's main memory, and something is needed to share data between CPUs and GPUs. Now, modern GPU runtimes such as CUDA provide abstractions like unified virtual memory to make it easy to program GPUs without having to worry about this management. Essentially, with unified virtual memory, the burden falls to the CUDA runtime system to move data between the GPU and main memory as need be. And this is fairly easy to use. You can replace calls to malloc in your code with a special, say, CUDA malloc managed function, which will allocate the buffer in UVM, and then allow the CUDA runtime to move the data between CPU and GPU as need be. And this keeps the user code simple. So this seems to be great. However, if you're in the room with anyone who's ever dealt with GPUs and you mention UVM, they will probably get up and shout, no, don't use UVM, it's slow. And they're not wrong. UVM can be very slow unless the user steps in and does something to explicitly move memory around, such as insert prefetch operations. And by slow, I mean the performance difference can be 100x. Just letting the CUDA runtime system move the memory as on demand versus performing some sort of prefetching. Now, if you're asking the programmer to insert prefetch operations all over the place, at that point it becomes really questionable. Why are you using UVM at all? Why not just explicitly manage your GPU memory? In our case, though, we asked whether there's some way that we can achieve both performance and simplicity. And in our case, we have a compiler on our side. And our compiler understands parallelism. And the compiler can reason about what memory is accessed inside these parallel loops that have been designated to run on the GPU. And so the Kitsune and Xera compilers will analyze those memory accesses inside parallel loops and automatically insert prefetch operations before kernel launches. It turns out the first iteration of this would just insert prefetch operations immediately before the kernel launch, which is approximately the dumbest looking thing you could do. And it turns out that works great. We get all of our performance back on our microbenchmark just by prefetching right before you launch the kernel. The compiler is capable of doing more, but we kind of need the examples in order to motivate us to do more. Now, Xera's UVM memory management doesn't stop there. It in fact implements some other optimizations for the sake of zero-knowledge proofs. For example, Xera will pool small allocations onto single UVM pages in order to avoid excess fragmentation within UVM. Turns out that when you allocate things in UVM, those are automatically 256 byte aligned. And so if you have a lot of small allocations, this can lead to bad fragmentation and performance degradation. So Xera addresses that just by implementing, at the moment, a simple bump allocator for UVM. Xera also looks through the compiler IR to identify bulk memory operations like memset, memcopy, and memmove, and figure out which of those operations are going to operate on GPU memory, and then replace those with GPU-friendly variants. Now, these operations will show up frequently in C++ code, courtesy of copy constructors, initializers, or calls to standard fill, or that sort of thing. And if you just let those run on the host side, which is what that function would imply, you incur a lot of excess memory traffic, which Xera is now able to avoid using some compiler analysis. We find that these two optimizations in Xera actually have complementary effects. For zero-knowledge proof systems with small numbers of input constraints, the small allocation pooling has a pretty sizable impact around 1.6x. But as we increase the number of input constraints, the impact of that small allocation pooling diminishes, largely because the GPUs become more, the kernels become more compute bound. On the other hand, as the input constraints grow, the cost of those bulk memory operations increases, and specializing those bulk memory operations to run on the GPU starts to pay off much more. Fortunately, these two optimizations are, like I said, complementary, and so Xera simply implements both of them to achieve the best of both worlds. Finally, Xera handles parallel reductions and ensures that parallel reductions can work with the same data types either on the CPU or on the GPU. And it does that by extending the linguistic mechanism to support reductions for reductions in OpenSilk. Turns out that when Xera takes a look at parallel loops that use reductions in the compiler IR, it can find the uses of those objects with special calls to intrinsics, which will in fact identify the identity and reduce functions that define that particular variable. And with that information, Xera then knows these are functions that need to live on the GPU, and it will proceed to synthesize appropriate reduction code for the GPU to handle that reduce operation. The reduction code performs a tree-style reduction. Xera first allocates an array in GPU shared memory, and then will perform tree reductions within a warp to populate the entries of that shared memory array, and then perform one more tree reduction on warp 0 to get a single view for the GPU block, and then finally resort to atomic cases to combine the views from distinct blocks. Xera also does something similar to handle scans using a new scan reducer hyperobject that we've added to OpenSilk. I think for the sake of time, I'm going to skip some more of the performance analysis and wrap up relatively quickly and come back to your question about how general are these extensions to task parallelism? How general are Xera's facilities for accelerating task parallel code? So in some separate work, we took Kitsuna with Xera's improvements and tried to parallelize a different code base, namely LAMPS. LAMPS, for those of you who don't know, is one of the primary software packages that the Department of Energy uses to perform molecular dynamic simulations. Now, we didn't parallelize all of LAMPS. All of LAMPS is like 1 million lines of code. It's a lot. But we did parallelize around 3,000 lines of code in LAMPS using these extensions. And that's enough for us to run some MD simulations. And so here I'm showing some of our preliminary results, just parallelizing LAMPS in this way and comparing against the existing GPU programming solution within LAMPS. And we find that, especially on simulations with increased size and complexity, we in fact perform better than that existing GPU programming solution within LAMPS, up to about 12% on the largest and most complex simulation we tested. I also want to point out that the existing GPU programming solution within LAMPS is basically a re-implementation of the LAMPS package wholesale to use that other programming platform, whereas our implementation parallelized some loops in otherwise serial code and then added some additional annotations. And that was about it. There are still a lot of things that Xera doesn't do. There are a lot of places where Xera's facilities won't handle fully general task parallel code, but I'm personally really excited about this work as I see it advancing performance and portability of task parallelism, that model of computation that we know and love, and simplifying software performance engineering to use novel parallel hardware. I think I'll wrap up there and take any questions.
Time for a couple questions.
So what's the example you've already encountered that it's not a good fit for?
An example that's not a good fit for, so we know we don't handle arbitrary nesting of parallelism. So for example, only the innermost loop is allowed to be a GPU parallel loop at this time. That's one that we're looking at because we think we can do better since we have the compiler on side, and it should be able to see multiple levels of parallel loop. But currently it doesn't, and I think that hinders its ability to handle, for example, some computations on multidimensional data. We also know that some of the strategies for managing UVM automatically won't handle arbitrary data structures. Like if you do pointer chasing, it's not necessarily, the compiler's not necessarily going to be able to figure that out and figure out everything to prefetch. Granted, the programmer can still add prefetch instructions themselves, but it's more burden on them. So those kinds of patterns.
All right, let's thank the speaker again. So in principle, there's a reception out there. We can go out and sing, so.